Professor and Byun and Young gentlemen for this conference. Okay. Today I am talking about possibly the last theorem in this direction about classical Calderon-Zsigmond theory. Okay. This is a typical second order elliptic equations in divergence form. So here, the non-homogeneous term F is assumed to be in LP space, and given data is the domain, and here the coefficient, the matrix. And the simplest case is the Laplacian equations. And of course, this is linear, so it has lots of invariance property, such as scaling, and translation, notation, and normalization. Okay. So, our main interest go to here the domain, open and bounded, and the matrix of coefficients is measurable, and the symmetric, and the elliptic, and the uniformly bounded. So, under this basic structural condition, we know that there exists a unique weak solution. And the question is, this is the typical Calderon-Zsigmond estimate. Here, P can be any number between 1 and infinite. And the question is, what might be the weakest condition to place on the coefficients? And what might be the lowest level of geometric condition on the boundary, so that we have this kind of Calderon-Zsigmond type estimate. Here, the good thing is P can be any number. So, actually, it is relatively easy if you allow the coefficient just continuous. But if the coefficient is not continuous, like a measurable, then this is a counterexample. As you see, this is measurable, right, in two variables. And it turns out that the Calderon-Zsigmond estimates does not hold true. Okay? So, this is a good thing that one can allow AX to be measurable only one variable. Okay? This is the lowest level of condition in the coefficients. And how about the boundary? And also this is a very well-known paper by Jellison and Kenny. Okay, they show that the estimate does not hold true if if the domain is a Lipschitz domain and the Lipschitz constant is sufficiently large. This is not true. And more precisely, if the domain is just a Lipschitz domain, then there is a bound. Okay, the two-dimensional case 4, and the three-dimensional case is 3. Okay. So the typical approach for this kind of a problem is like this. Okay. So let's start with a priori estimate, assuming that everything is nice enough. So the matrix is continuous and the boundary is sin 1, 1. And then, of course, you can localize, right, by using some cover function. And you can, here, you can select any point and any sufficient small size are here. Then you can transform this kind of equation. And the good thing is that here the coefficient is just a constant coefficient. Okay, so if we can control the equation with a constant coefficient, at the same time, if we make, like here, this norm sufficiently small, then this norm here, right? If this is sufficiently small, then this term can be swallowed by this term to obtain this kind of estimate. Okay, so that is a hope here. Here, this is a constant coefficient, and this is a BMO semi-norm. Then the question is how we can improve, okay, these two items. Okay, so of course here, this norm is sufficiently small. If this is equivalence, BMO semi-norm is sufficiently small, or strongly say that A belongs to BMO, then we have this kind of LP estimate. So let me go here. So that is hope here. Just relax from constant coefficient to the equation of like just one variable dependent coefficient. Also here BMO semi-norm is for all variables. If you can relax to just, if you can make just one variable to be free condition, at the same time the other variables small BMO condition, then this might be the, I think that the best condition, optimal condition for this kind of problem. Okay, so that is here. In the previous result, we have used this one. The limiting problem is the equations with a constant coefficient, and the BMO semi-norm is sufficiently small. Now this is a little bit improvement. Okay, so the equations here we allow one variable, just a precondition. So this equation has coefficients which is dependent on only just one variable. And here, BMO semi-norm, this is a weakly BMO semi-norm. That is, one variable is a pre-constant, precondition, and the other variables, with respect to the other variables, this is BMO semi-norm is sufficiently small. Okay? So how about the issue of the boundary? Of course, we need some placement argument in the classical approach. So starting point is you can start just the Plato domain. Okay, then Lipschitz domain is better than. Also, the natural extension of Lipschitz domain is so-called Reifenberg domain. And it turns out that this kind of domain is the optimal domain for the W1P extension domain. So here you cannot improve more than Reifenberg domains. So this is our hope. A is just measurable in one variable, and with a small BMO semi-norms in the other variables. And the boundary of my domain is locally flat in the Reifenberg set. This means that with a small deviation from the hyperplane at each point and at each scale. Okay. So our approach is based on the perturbation theory. Okay, so first, so this is the W1P estimate. So the limiting case, P goes to infinite. W1 infinite regularity, that is a Lipschitz regularity. So at least we need a Lipschitz regularity for the limiting problem. Okay, the equation with a one variable dependent coefficient on the flat domain, because the Reichenberg flat domain can be approximated by hyperboundary. And this is a perturbation. So this is given okay, sorry, this is typo. And later, you have to use you will use the maximal function of rate and vitally covering them. Okay, so the standard notation is that, so if you are standard in some domain, right? So at point, at each scale, right, the condition is there exists some coordinate system. So one variable is a free condition, and the tangential direction is we have to control by using BMS and norms. So that's why you need this condition. So tangential direction, you have a small ball, and xn direction from like minus r plus r. That's why I have this kind of so-called, let's say this is the elliptic cylinder. Okay, this is averaging. And here, the most important part here, so xn slice. Okay, xn, so this is a pre-domain, and on except the other variables, let me denote by x prime. Okay, so this is the integral average on the xn slice. Okay. So the BM space, right? This is a typical definition, BM space and the VM space. Most of you are very familiar, right? Is the analysis and the partial differential equations. So let me skip this definition. And the BM space is appropriate of the substitute for L infinite when L infinite does not work. So this is a relation between L infinite and the BM space and the BM space. Also the maximal function, right? This is the definition. Also you can use also sharp maximal function. And the good thing is this function is invariant with respect to scaling. And there is two important property of maximal function. But this is a weak 1-1 estimate. This is a strong PP estimate. So you say that if f belongs to LP space, then maximal function belongs to LP space. Of course, if this belongs to LP space, then f belongs to LP space. And so Reichenberg domain, the definition is here. So at each point on the boundary, and at each scale, right, there exists the two hyperplanes here. So this part can be tracked into two hyperplanes. This is exactly, just you can roughly say that the boundary at each point, at each scale, the boundary can be approximated by hyperplanes. This is some well-known property regarding Reichenberg flat domains. Okay, so here its boundaries are locally close to disk in all scales, and the boundary can be fractals. And there are several approaches to this Calderon-Zygmunt estimate. And the classical one is by using the potential theory, right? Like if you have equation with a constant coefficient, then you have the representation formulas, right? Then you can play with some functional analysis frame here. But the limitation for this problem is this approach cannot work for nonlinear problems, right? Because you have the fundamental solution for the nonlinear problems. Or if the boundary is beyond the Lipschitz domain, then you cannot use the flattening argument, something like that. And the best result by using this kind of a potential theory is just A belongs to Byun space, and the boundary belongs to C1 space. And another approach is using maximal function approach. Actually, this approach is developed by Caprelli and Perel about 10 years ago. But still, this approach has some limitation, right? Because this maximal function is strongly dependent on the invariance of the scaling. If the equations are not invariant on the scaling, then we cannot apply to these problems. Like P Laplacian parabolic equations, the scale is different between time and the space. So this is a little bit limitations. And by using this approach, we have some result here. A has a sufficiently Byun seminorm, and the boundary omega is a Reichenberg domain, then we can find a W1P estimate. And another approach is, this is also very powerful approach. Very recently, Professor Krloff at the University of Minnesota and his students, they used this approach. This is a pointwise estimate by using sharp maximal function. And W here, that is the property like a W1P estimate and the strong PP estimate. But it's somewhere, as far as I know, they have to use this Fourier transform. It means that if the problem is nonlinear, then you cannot keep going. Okay, so this is a little bit limitation. So this is not work for nonlinear problems. At the same time, also, if the domain is beyond the Lipschitz domain, also you cannot use that. But on the other hand, by using this approach, they let the coefficient here the small partial PMO is exactly the same condition as I am talking today. Just one variable is just a measurable, and the other variable is a small variable condition. Also, for the case, if the problem is the PDE has no scaling property, right? Then we cannot use like a maximal function or a sharp maximal function, right? In this case, also recently, Italian mathematicians, they developed the so-called maximal function pre-technique. And so here, in this approach, they don't have to use the maximal function approach. Okay, this is very nice. But still, this is a pointwise estimate. That is a priori estimate. So the most difficult part here, if the domain, the equation is highly nonlinear, and the domain is like beyond the Lipschitz domain, usually like approach argument is very delicate and very difficult to reach a general case. But I do believe that this kind of P Laplacian type parabolic equations maximal function is not working, but by just using and modifying their approach, recently you could find a W1P, optimal W1P estimate for P Laplacian parabolic equation, not system. For the systems, we have no idea. And the assumption is exactly here. Right? Because our problem is a scaling invariant at each point, at each scale, is the exact, at each point, exactly, at each scale. Right? There exists some coordinate system. And one variable is a pre-constant here, precondition, but with respect to other variables, this is the definition. Exactly, the definition is partial BMO seminoids. Right? How about near the boundary? Near the boundary, exactly the same argument can be applied here. And this is the main theorem. So given P can be any number, there exists the small delta, should be universal constant. And if, like here, A of x has a small BMO seminorms except one variable, but still you can make free conditions in the one variable. Also, the domain is a Reichenberg flat domain, and you have a W1P estimate. Okay. So I do believe that. So I think that you cannot improve this result in the sense that if you allow two variables to be measurable, then you have a counterexample. Also, Reichenberg domain is the optimal W1P extends domain. So who knows, but I do strongly believe that this is the last theorem in this direction. So the most difficulty to us is to show that the Lipster regularity for the limiting problem, which has one dependent variable coefficient. So, and this is a very delicate and very complicated. Let me write down here. Ij is the index from 1 to n minus 1, and assume that n bigger than or equal to 3. N equals 1, n equals 2 is the easy problem. And also summation notation is used. Okay, this is our limiting problem. As you see, the coefficient is only dependent. Only just one variable. You can say xn. Okay. So instead of using this elliptic operator, so let's use this L plus operator. Okay. So L plus operator is like this. So this is A is n by n matrix. Let's say this is Aij, and this A and n, and this A1n, A1m minus 1, and A and n1, an n minus 1. This is the matrix, and what is the matrix to the related L plus? Let's say this is L plus, and this part, this is just 0. Okay. This is the matrix related to L plus operator. The purpose is to show that the Lipster regulative for this limiting problem. Probably there should be a very simple and easy way, but we don't know. we just use this operator, L plus operator. Okay. Then, by using the direct computation, we can show that this L plus operator is still elliptic. Then, since L plus is elliptic operator, then we can use just the standard, like L2 estimate for this equation with one dependent variable coefficient. Okay? So let's start with this equation, the boundaries. And with respect to tangential direction, because the coefficient has only dependent on xn variable, so along the tangential direction, this has C infinity regularity. And also, okay, so if the right-hand side, the non-homogeneous term is dependent only xn variable, then we can show that the solution is locally ellipse continuous. And of course, this can be extended. You can add this term. And for the up to the boundary, then we need this kind of lemma, right? Because we need some reflection argument. Then, if G belongs to L infinite space, with the Aij is the tangential direction, Hessian tangential Hessian in the tangential direction belongs to L infinite. Then has a ellipse regularity. And finally, we can show this one. Actually, this is a very, very delicate and very complicated, but fortunately, we finally have a proof for this regularity. And once we have this theory, then we can apply to our previous technique exactly, in the same plane. So there are two cases, right? Interior estimate and the boundary estimate. And for the interior estimate, okay, there exists some universal constant here. This is the condition. This means that if you have one good point, working point means that gradient U squared is uniformly bounded, and f is sufficiently small. This means that you have one good point, then lots of, you have almost everywhere, you have good point there. Right? So the most important part for the W1P estimate is here. And how to find like the power decay estimate of this level set. This is interior estimate, and the proof is here. V is the solution of the limiting problem, which has the least regularity. And we can show this one. And this is the computation, right? du square, blah, blah. So here we can control the measure of this level set as small as we want. And near the boundary estimate, by using our condition so that the boundary is locally can be approximated by hyperplanes, like something like that. This is the conditions, sufficiently flat and partially small beyond sometimes. But exactly the same here. Same. Okay. And this is our covering lemma. Exactly the same. This is very similar to classical Calderon-Zygmunt estimate. Calderon-Zygmunt covering. Then once you have this one, then the conclusion is here. So directly by applying to this covering lemma, okay, this is the conclusion. Okay, this is one condition. because our problem is linear. Right? So by normalization, of course, we can assume this one. And the second condition has, by using the perturbation theory, already we have shown this one. Then the conclusion is here. And the iteration, by iteration, we can show this one. Okay, so once you have this kind of the power decay estimates for the level set, then you are almost there, because this is direct computation. Okay, this is a power decay estimate, and this is answer one is a universal constant. Then you can reach here. If you can take this number, it's a strictly less than 1, this is a finite number. Okay, here. So if we select this number is strictly less than 1, then we have this one. Okay? And this, which implies that the classical Calderon-Zygmunt type estimate for the divergence equations. Okay. And the possibly related problem, by using exactly the same technique, you can solve the parabolic equations. The same with the measurable coefficient in time-dependent random movements. Also, you can go to the systems. So this problem and this problem is not difficult. You can do that. It's almost finished. But for this kind of nonlinear problems, like elliptic and parabolic equation system with a measurable nonlinearity, it might be really difficult problems. But I hope somebody in the future can solve this problem. So, okay, thank you very much. I have to stop.
Any question or comment? Okay, maybe your